Hello, welcome back. And once again, this is my fourth presentation of this series on lithium-ion batteries. Today's presentation will focus on the reactions of the electrolyte with the cathode materials. With that, let me go to my presentation. Okay, so today's presentation, as I said, is on the reactivity of the electrolyte with cathode materials for lithium-ion batteries. And so in terms of the cathode electrolyte interface within lithium-ion batteries, this has received much less attention than what is observed for the anode solid electrolyte interface. Part of this is due to the understanding and the importance of the anode SEI was observed immediately, because if you did not generate a good SEI on the anode, the cells rapidly had rapid capacity fade and basically no longer functioned pretty rapidly. However, the cathode electrolyte interface is typically really only observed in a significant capacity or significant form after more long-term cycling. And certainly in the earlier times of lithium-ion batteries, where the lifetime of the batteries was not particularly long, 100 or 200 cycles, the interface on the cathode was not as significant of a problem as on the anode. However, in modern lithium-ion batteries, where electric vehicle applications and long-term applications such as grid scale storage is critical, and also the development of high voltage cathodes for consumer electronics is critical, the reactions on the cathode have become much more important. So basically, accelerated aging experiments suggest that there is a significant amount of impedance growth on the cathode. And in fact, the impedance growth in the cathode is the primary source of the impedance changes within cells. Also, since, as I said, there's a large interest in development of higher voltage cathode materials, upon shifting these cathodes to higher potentials, typically what happens is you end up with more electrolyte oxidation reactions at the surface of the cathode, which has generated a significant increase in our understanding of developing electrolytes with better stability at high voltage. And so basically, because of these detrimental reactions of the electrolyte with the surface of the cathode materials, it's really limited the ability of cathode materials to be used at extremely high voltages, so above 4.5, 4.4 volts. One of the things that's been attributed, or was earlier on attributed to this problem, is that there's transition metal dissolution from the cathode, and that was perceived to be a problem, although why it's a problem and what caused the problems was not very well understood. And then something else that was observed early on was that if the cathode materials were coated with an inert material such as silicon oxide or aluminum oxide or titanium oxide, that this typically improved the performance of cathodes when going to higher voltage. So our initial investigations into these materials really focused on the thermal reactions initially, and then we expanded our investigations to include electrochemical investigations. And as I reported in previous presentations, the thermal dissociation of LiPF6 is a significant problem for LiPF6-based electrolyte formulations, of which most all commercial lithium-ion batteries contain LiPF6. And LiPF6 decomposes to generate PF5, which is a strong Lewis acid, which can cause polymerization of ethylene carbonate and other problems within the cell. The initial generation of PF5 can initiate an autocatalytic decomposition mechanism, as we've already stated, which can generate high concentrations of phosphorus oxyfluoride. And this phosphorus oxyfluoride is also a very strong Lewis acid, which can cause decomposition reactions in the electrolyte and cause decomposition reactions at the surface of the electrodes. So what we observed in our initial investigations of the electrolyte upon thermal treatment of the electrolyte with basic cathode materials. And so basically all we were doing is taking the pure fresh cathode materials and storing these cathode materials in the presence of the electrolyte. Most of the cathode materials, including lithium cobalt oxide and lithium nickel cobalt oxide, contain a thin layer of lithium carbonate on the surface. This is true for all NMC materials also. And when you store these materials in the electrolyte at moderately elevated temperatures, 70 degrees centigrade for a couple hours, for a day, or 50 degrees centigrade for a few weeks, basically this lithium carbonate layer is dissolved and removed from the surface for the most part, and you deposit a layer of electrolyte decomposition products, which include polyethylene oxide, lithium fluorophosphates, lithium fluoride, and along with transition metal fluorides. And so this is kind of an etching reaction, which is attributed to the presence of these acidic species, such as phosphorus oxyfluoride, PF5, and also potentially HF being generated from the decomposition of the electrolyte, which can result in the deposit of electrolyte decomposition products on the surface, but then also an etching and a corrosion effectively of the metal surface. So upon looking at these surfaces with SEM imaging, what you can see is that basically before storage, the cathode particles look pretty crisp and clean and nice edges. And after storage, you can really see that there's a lot of electrolyte deposition on the surface. We also can observe a significant amount of manganese dissolution for the lithium nickel manganese oxide materials, which is confirmed by ICP-MS. And as I said, these initial experiments were done at relatively high temperature for a short period of time, but similar results were observed for longer term storage at moderately elevated temperatures, such as 55 degrees centigrade. Once again, this suggesting that over the lifetime calendar life of the battery, these kinds of thermal decomposition reactions are going to be contributing to the overall performance fade of these lithium nickel manganese oxide cells. So if we look at the XPS, X-ray photoelectron spectra of these surfaces, what we can see is the fresh cathode particles have high concentrations of metal oxide and low concentrations of lithium carbonate. However, after storage, we see a whole range of lithium fluorophosphate species, along with a little bit of lithium fluoride, and a decrease and other oxygen-containing species, and a net decrease in the concentration of the metal oxide peak. What this suggests is that the original metal oxide surface is now being covered with electrolyte decomposition products from this thermal decomposition of the reaction and thermal etching of the surface of the cathode particles. So at the time, one of our thoughts in order to improve the performance of overall cathode materials is that we could develop a series of Lewis basic additives. So since we know that phosphorus oxyfluoride and PF5 are both very strong Lewis acids, and we know that carbonate solvents are Lewis bases, and therefore this acid-base reaction leads to the decomposition of the carbonate solvents by this autocatalytic decomposition mechanism. If we are able to develop additives that inhibit this acid-base interaction from the carbonate solvents, that then generate some stable species, then that may slow or stop this thermal decomposition reaction of the electrolyte, and also the thermal decomposition reactions on the surface and the etching of the cathode particles. So with this in mind, we went back and did a similar experiment with the lithium nickel manganese oxide, storing it in the presence of the LiPF6 with and without Lewis bases. And what we can see is the fresh cathode particles, once again, have very nice, crisp, clean edges. The standard electrolyte formulation, we see a lot of corrosion and also deposition of electrolyte decomposition products. However, in the presence of the Lewis base, we see basically very, very similar cathode particles to what we had with the fresh materials. And once again, these are not cycled cathode particles. These are just the fresh cathode particles, and we're really just focusing on isolating on the thermal reactions that occur here. Now, at the same time, while we see a lot less electrolyte deposition on the surface of the cathode with the basic additive, we also see dramatically lower transition metal dissolution, both manganese and nickel. The dissolution of these species is inhibited which is once again consistent with limiting the corrosion of these cathode particles. So if we look at the XPS of the uncharged lithium nickel manganese particles with the LiPF6 carbonate solvents with and without bases, once again, after the storage, we can see, as we saw previously, that there's a lot of electrolyte decomposition on the surface with the standard electrolyte upon thermal storage, and we see much less lithium transition metal oxide. However, in the presence of the Lewis base, we see much less electrolyte decomposition products on the surface of the material. We see much lower concentrations of the oxygen species characteristic of these decomposition products, and we see much higher concentrations of the transition metal at the surface, or transition metal oxide at the surface, which once again confirms that these Lewis basic additives are inhibiting the generation of these acidic species, such as PF5 and phosphorus oxyfluoride, and that this results in a decrease in the reaction of the electrolyte and the deposition of the electrolyte decomposition products on the surface. So with this moves us on to now looking at the electrochemical effects. And so a lot of these thermal effects that I first showed were on a range of different cathode materials, including lithium cobalt oxide, lithium nickel manganese oxide, high voltage spinel, and also the lithium nickel manganese, nickel cobalt oxide. In this case, now we'll start and we'll look at a lot of the electrochemical effects of different cathode materials. And so in terms of the presentation, we're first going to look at the effect of electrolyte and electrolyte additives on the high voltage spinel, the lithium nickel manganese oxide, and then we'll follow with the more commonly utilized NMC materials, the layered metal oxides, and then finally with the overlithiated manganese-rich materials. So in terms of the high voltage spinel cathode materials, there are two primary mechanisms that had been reported for performance fade, capacity loss, impedance growth due to the presence of electrolyte. And the first one was the oxidation of the electrolyte on the cathode surface. And the second one is transition metal ion dissolution due to these acidic electrolyte decomposition products. And so in terms of this, what we wanted to do was investigate novel electrolyte additives to improve the performance of these high voltage cathodes. And basically there were two different methods that we have been looking at in order to do this. First off, there's a cathode film forming additives. So basically if we add an electrolyte additive, which can be sacrificially oxidized on the surface of the cathode to generate a stable cathode passivation film, this type of electrolyte additive could be beneficial to the overall performance. Alternatively, we have looked at acid scavenging additives, similar to what I just presented right before this, in terms of the additives inhibiting the thermal decomposition of PF6 anions, which generates acidic species, including HF, or absorbs residual acidic species such as HF or phosphorus oxyfluoride that might be generated during cell cycling via, say, the generation of water from decomposition reactions. So our initial experiments in this area looked at the overall residual current flow within cells, which contained delithiated lithium nickel manganese oxide, or just nickel manganese oxide. In this case, if we store these cells at very low potentials for a very long period of time, what you see is there's basically virtually no residual current flow in the cells. However, if you store the cells at high potential, 5 volts or 5.3 volts, we see a very large amount of residual current flow. Since these materials are already delithiated, basically what we have are only the side reactions of the cathode material with the electrolyte and not any delithiation reactions. And what we can see is these residual current flows coincide very well with the generation of carbonate type species which contain carbon-oxygen double bonds or carbon-oxygen single bonds by XPS spectra. We also see a decrease in the overall concentration of the transition metal oxide. And by IR spectroscopy, what we can see is that these new species that are generated on the surface are predominantly polyethylene carbonate. So under these conditions, once again, this is relatively high voltage, what we observe is a primary decomposition reaction is the decomposition of ethylene carbonate to generate polyethylene carbonate on the surface of the cathode materials. So we were concerned about these electrolyte oxidation reactions on the surface of cathode materials, and so we started to try and investigate electrolyte additives that might improve the overall performance of these high voltage cathodes. And the first one that we found was lithium bisoxalato-borate, which is an electrolyte additive that I've mentioned previously in the past presentations. Also was an alternative salt that was investigated for lithium batteries. And in this case, if we add 1.5 or 2.5% by weight of lithium bisoxalato-borate, the structure here, to the standard electrolyte formulation, which is once again 1 molar LiPF6 and ECEMC 3 to 7. What we see is that basically the capacity fade of the material storing at elevated temperatures, which is 55 degrees centigrade, is much lower in the presence of the electrolyte additive, LIBOB, than it is for the standard high voltage spinel. We were looking at the storage of these materials or the cycling of these materials at moderately elevated temperature because that was really one of the primary problems with the lithium nickel manganese oxide, the high voltage spinel, is that they have very poor capacity retention at moderately elevated temperatures. And so that was the focus of these investigations. And we were very pleased to see that the additive inhibited the capacity loss for these materials. However, we weren't particularly pleased when we observed that the LIBOB really didn't improve the overall efficiency of the cells. And so while the capacity is retained, we still have poor efficiency, which suggests that there's still some problem within the cell. But nonetheless, we wanted to utilize LIBOB as an additive for an investigation to try and understand why and how LIBOB stabilizes these improves the capacity retention, so then we might be able to go back and design better additives than LIBOB. At the same point, I should point out that in addition to the improvement of the overall capacity retention, LIBOB also significantly reduces the manganese dissolution, which is a significant problem for these cells. So if we go back and we look at the TEM images of these cathode particles after storage at elevated temperature, and what we can see is the fresh cathode particles have very nice, crisp, clean edges, while the cathode particles with the standard electrolyte cycle, these are just at 25 degrees centigrade, shows that we see a significant amount of deposition of electrolyte decomposition products on the surface, which are high in both concentrations of fluorine and oxygen and carbon, much higher than what the standard electrolyte, the cathode material, the interior cathode material are. And if we continue cycling these at 55 degrees centigrade, you can see even more surface damage to the cathode materials and more electrolyte decomposition, and also it appears to be kind of a corrosion of the cathode particles themselves. However, in the presence of the LIBOB, what we can see is that basically the surface is much better retained. There's a little bit of damage to the surface, but it's much better retained than it is in the case of the standard electrolyte formulation, and consistent with the better performance. We see this surface film retained both at cycling at 25 degrees and then also for the cycling at 55 degrees. In both cases, we see a significant reduction in the damage to the surface and also to the deposition of electrolyte decomposition products on the surface. And so clearly the LIBOB inhibits the surface damage, and the inhibition of the surface damage is consistent with the improved cycling performance and the decrease in manganese dissolution. However, if we go back over on the anode side and look what's happened to the anode, we see very similar effects, in that basically our fresh anode particles have nice, crisp, clean edges. The standard electrolyte cycle at 25 degrees centigrade, you can see the generation of a SEI on the surface of the graphite, as you would expect, with low concentrations of oxygen and fluorine on the surface, a little bit of manganese and nickel. However, when we cycle the standard electrolyte at 55 degrees centigrade, what we can see is very, very high concentrations of manganese and nickel. And once again, we see a very, very thick and uneven anode surface film, suggesting that at these high temperatures, the anode surface film is significantly damaged without LIBOB. However, in the presence of LIBOB, we see a nice, crisp, clean SEI formed on the surface of the film after cycling at 25 degrees centigrade, and we don't really see a significantly large change upon cycling at 55 degrees centigrade, and the manganese concentration, once again, is very much lower than it is for the standard electrolyte formulation. Once again, suggesting that the presence of the LIBOB is inhibiting transition metal dissolution from the cathode side and then deposition on the anode side, and also it's inhibiting damage of the anode SEI, which is presumably occurring via either transition metal catalyzed decomposition reactions or the generation of acidic species from the surface of the cathode. So if we look at the online electrochemical mass spectroscopy of cells containing the high voltage spinel, which we did in collaboration with Hubert Gasteiger at TU Munich, what we can see is the cells which contain LIBOB, we see a large amount of gas evolved, which is predominantly CO2, which is consistent with LIBOB oxidation at high potential and the generation of a cathode surface film from this sacrificial oxidation of LIBOB on the surface of the cathode. So if we look at the comparison of the initial 3 charge discharge curves for lithium nickel manganese oxide high voltage spinel cathode cells for the standard electrolyte formula versus the LIBOB formula, and if we look at the lower potential only going up to 4.9 volts, we see fairly similar charge discharge curves. However, if we go to a much higher potential all the way up to 5.4 volts, what you can see is that the LIBOB basically stops and you don't have a lot of residual current occurring up here at the high potential. However, without the LIBOB, with the standard electrolyte formulation, we see a large amount of residual current flow at these high potentials. So what this suggests is that the presence of the LIBOB is generating a passivation film on the cathode, which is inhibiting these residual current flow reactions, which is inhibiting these electrolyte decompositions or electrolyte oxidation reactions that are occurring at the high potential. So if we look back at the surface of these lithium nickel manganese oxides after storage experiments similar to the ones before, the cycling experiments, these initial 3 charge cycling experiments. And what we see is that for the standard electrolyte formulation, we don't see much of a change compared to the fresh cathode particles when we cycle the cells to the 4.9 volts by either IR spectroscopy over here or by XPS spectra on the left. However, if we store the standard electrolytes to 5.4 volts, we see a very large change in both the XPS spectra and also the IR spectra, consistent with the generation of high concentrations of polyethylene carbonate. So we're seeing a lot of polymerization reaction here. In the case of the LIBOB, by XPS and also by IR, we see small changes upon cycling to the 4.9 volts, which is consistent with the sacrificial oxidation of LIBOB to generate a cathode passivation film. However, when we go up to 5.4 volts, we don't really see a very large change in the case of the LIBOB, the electrolytes containing LIBOB, which once again is consistent with the fact that at 4.9 volts, we have oxidized LIBOB to generate a cathode passivation film, and that this cathode passivation film inhibits further electrolyte oxidation at the higher potentials. So the kind of summary here of our investigation of LIBOB is that LIBOB is clearly sacrificially oxidized on the surface of the cathode, which generates CO2 and also forms a cathode passivation film. The addition of LIBOB inhibits manganese dissolution and also electrolyte oxidation, and that LIBOB can improve the capacity retention upon cycling at 55 degrees centigrade. Unfortunately, it does not significantly improve the overall efficiency, which we'll see some other additives shortly. And basically what we believe is the oxidation of LIBOB generates a neutral radical species, which was proposed by Daniel Abraham and coworkers, which undergoes this kind of polymerization reaction or oligomerization reaction of the LIBOB species to generate a borate-based surface film, which passivates the surface of the cathode. So with this in mind, we were really interested in trying to develop a better additive, because while LIBOB did improve the performance of these cathodes, the efficiencies were still not very high, and the oxidative decomposition of LIBOB generates CO2, which is a gas, which would cause problems with cell gassing and pressure within the cell. As we were working on this project at a DOE program review meeting, some results were presented by Oleg Borodin, who suggested that from molecular dynamic simulations, that when cells are polarized, so when you try to charge cells or polarized cells, what happens is that the anions are polarized towards the surface of the cathode, and that the cations are polarized towards the surface of the anode, which makes sense and is fairly obvious. However, it hadn't occurred to me before this that you might be able to utilize this as a method to design electrolyte additives. So we can take advantage of the fact that the cell polarization results in the migration of anodes towards the cathode by trying to design anionic-based electrolyte additives. Because if we have an additive which is anionic, it's both going to be polarized towards the surface of the cathode. It's also going to be electron-rich, which is going to result in a more easy oxidation of the material. And this can be observed by the differences between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, where if we're trying to oxidize the material, we're wanting to have higher level homos, which can then allow us to more easily oxidize the material, which is what we observe for these borate-based anions here, which are desirable materials such as LIBOB. So with this in mind, it occurred to us we might be able to make tetraalkyl substituted borates that might be useful anionic additives for lithium-ion batteries. And so with this in mind, the first additive that we made was lithium tetramethyl borate. It's a very simple synthesis. We do a lot of synthesis of compounds in my laboratory. And so if you take trimethyl borate and react trimethyl borate with lithium methoxide, you can generate lithium trimethyl borate. When we add the lithium trimethyl borate to the lithium nickel high voltage spinel cathodes, what you can see is evidence with the new peak being observed in the presence of the additive, where the trimethyl borate is being oxidized on the first few charging cycles, or the first charging cycle. And what this results in is somewhat of a better capacity retention with the lithium tetramethyl borate than with the standard electrolyte formulation. While this was not as good of improved performance as what we observed for the LIBOB, it was nonetheless promising and encouraged us to look further at developing borate-based additives for borate-based additives as high voltage electrolyte additives. When we do the surface analysis of the material, what we can see is that basically, look at the surface of the lithium nickel manganese oxides cathodes. The fresh cathode is a very high level of transition metal oxide, while we have low concentrations of lithium carbonate. With the baseline electrolyte, what we see is a very large decrease in the concentration of the transition metal oxide, consistent with the deposition of electrolyte decomposition products on the surface. In the presence of the lithium tetramethyl borate, we see not as thick of a surface film because we see more transition metal oxide on the surface, and we also see boron present on the surface, consistent with the oxidation of these borate additives on the cathode surface. This enabled us to go forward and design a whole series of different cathode additives or high voltage additives based on this same analogous strategy. So we could take a series of different lithium alkoxides of all of these different compounds and react them with trimethyl borate to make the trimethyl borate alkoxide version of the electrolyte additive. So since, once again, the trimethyl borate is compatible with lithium-ion batteries, we synthesized a whole series of these lithium trimethyl monoalkoxide-based borate additives, and we can use these as a functional group delivery agent. So if we want to have some polymerization reaction occurring by adding a alkene or an alkyne, or if we want to add a cyanosubstituent, or if we want to add various types of aryl groups on the surface, or pyridine group as a Lewis basic species, we can generate a selectively functionalized cathode surface film by the design of these novel borate additives. We were able to prepare over 50 different novel borates. We were able to prepare these materials in high yield. They're relatively easy to purify, and they have reasonable solubility for the levels of which you want to incorporate electrolyte additives into standard electrolyte formulations. So these have good solubility from 0.5 to 2 weight percent of the materials. The anionic species migrate to the surface of the cathode, as I already mentioned, upon polarization. And once again, this allows us to selectively functionalize the surface of the cathode with whatever type of functional group that we're wanting to put on the surface of the cathode that we think might inhibit the detrimental reactions of the electrolyte with the cathode surface. So once again, just for an example, we can characterize all of these different aryl trimethyl borate species by NMR spectroscopy. As you can see from the proton, carbon-13, and boron-11 NMR spectra, these species are very clean. There's really nothing else that are present in these spectra other than the compounds that are desired. And as I said, they can be made both in high yield and also high purity. So when we incorporated these lithium alkyl trimethyl borate species into the graphite lithium nickel manganese oxide cells, what we observed was both a significant improvement in the capacity retention upon cycling at 55 degrees centigrade, and also for the first time in our observation, we see also a significant improvement in the overall efficiency. So what this suggests is that not only are we shutting down the decomposition reactions or slowing the decomposition reactions that lead to capacity fade, we're also inhibiting the decomposition reactions that lead to poor efficiency. And so this is really critical in terms of developing a viable electrolyte formulation for this system. It also these additives also significantly inhibit manganese dissolution and also electrolyte oxidation on the surface of the cathode. Fortunately, also for these materials, which is always a critical concern when developing novel electrolyte formulations, is that the presence of the electrolyte did not affect either the rate performance or the low temperature performance. Frequently, when you develop novel electrolyte formulations, while it may improve capacity retention and thermal stability, or it may improve the efficiency also, at times these additives can generate relatively thick surface films, which then adversely affect the low temperature performance or the rate performance, so trying to charge and discharge at high rates, and this becomes significantly problematic. So as I said, much like what we had with the lithium tetramethyl borate, when we look at the lithium pyridyl trimethyl borate, we see an oxidation peak on the first charge cycle at about 4.5 volts on a glassy carbon electrode, which is consistent with the oxidation of our additive, which is what we're looking for. We're wanting to sacrificially oxidize these cathode materials on the surface of the electrolyte additives on the surface of the cathode to result in a passivation film. And what we see once again is there's really no change in the overall rate performance, and there's no change in the low temperature performance of the materials. So if we go and take the cells apart after cycling, what we can see is very similar to results to what we observed for the LIBOB. With the standard fresh cathode material, we have a very nice crisp, clean edge. For the cathode with the standard electrolyte formulation, we see a large amount of damage to the surface of the cathode, a lot of corrosion. We also see significant etching of the materials. However, in the presence of the lithium borate additives, we see basically a much smoother surface film with much less damage. We also see by XPS spectroscopy the presence of boron on the surface, which confirms that these materials are being sacrificially oxidized, and then by being sacrificially oxidized that they're generating a passivation film, which inhibits the overall electrolyte oxidation. Now on the anode side, we see similar results to what we observed with LIBOB again, is that the fresh anode, we see nice, crisp, clean graphite in the presence of the standard electrolyte formulation cycled at room temperature. We see SEI formation, but for the anode cycled at elevated temperature, we see both SEI generation and very much of an SEI damage and very thick SEI with, once again, very high concentrations of manganese and of nickel. However, in the presence of various different types of lithium alkyl or lithium propargyl or lithium aryl trimethyl borate species, what we see is a very nice, smooth anode surface film and relatively low concentrations of manganese. Once again, consistent with the fact that the presence of our electrolyte additive is inhibiting transition metal dissolution from the cathode and deposition on the anode, damaging the anode SEI. So the summary for this section of the talk is basically for these lithium nickel manganese oxide cathodes, the electrolyte oxidation, it generates polyethylene carbonate on the surface of the cathode film at high potentials. The LiPF6 based electrolytes can dissolve manganese at these elevated temperatures and etch the surface, corrode the surface of the lithium nickel manganese oxide cathode. The additives can inhibit the formation of the polycarbonate on the surface of the cathode and also inhibit manganese dissolution. The lithium nickel manganese oxide cathodes improve both the cycling performance at higher voltage and elevated temperatures. We developed a series of tetra-substituted borates as novel electrolyte additives. One of the interesting aspects with these tetramethyl borates is that we can easily modify the structure of the tetramethyl borate to utilize these borate additives as surface functionalizing species to tailor the reactions on the surface of the cathode and tailor the functional groups that are delivered to the surface of the cathode. And the tetra-substituted borates improve the stability of the LiPF6 carbonate electrolytes as a bulk material. At the beginning of this talk, I mentioned that LiPF6 has thermal stability issues, where if you heat it in the presence of carbonate electrolytes, these electrolytes can decompose. These, in addition to being oxidized on the surface of the cathode, these tetra-substituted borate additives also inhibit the thermal decomposition of the LiPF6 based electrolytes in the bulk solution. So this is an additional benefit of the additive. So with this, it brings us to the next type of cathode, which are the NMC cathodes, the nickel manganese cobalt based cathode systems. There's a lot of interest in the development of these NMC based cathode materials, and these are the most widely utilized cathode materials in commercial lithium-ion batteries today. And these cathode materials typically function quite well at standard lower voltages, such as charging the cells to about 4.1 or 4.2 volts. However, in current interests in lithium-ion batteries in terms of making higher energy density batteries, there's a significant interest in driving these NMC cathodes to higher potentials above 4.2, closer to 4.3 or 4.4 or even 4.5 volts. When you try and shift these cathode materials to higher potentials, what happens is that you start to see more electrolyte decomposition reactions, and you see a significant decrease in cycle stability. At the same time, as I mentioned in the first presentation, there's a big interest in moving away from cobalt to higher nickel content NMCs. When you go to higher nickel content NMCs, the increase in nickel content also tends to lead to an increase in negative reactions with the electrolyte and the decomposition of the electrolyte and poor cycling performance. So both of the things that are of significant interest to the battery community right now, shifting towards NMC materials with higher nickel content and shifting to NMC materials or cycling the NMC materials to higher potential, both are problematic in terms of their reactions with the electrolyte. And so what we've been focusing a lot of our efforts on over the last 5 or 6 years is trying to understand what is the role of the electrolyte in these performance decreases, and what is the role and how does changing the potential or changing the nickel content change the overall reactions with the electrolyte. And so what is generally believed is that you have a highly reactive surface, which leads to the reaction of the cathode material with the electrolyte. In addition to these reactions with the electrolyte, there are other concerns on the cathode side, which won't be covered in my presentation, but have been reported and reviewed in this article in the Journal of the Electrochemical Society. These other issues include that when you go to high nickel content, this can lead to lithium nickel cation mixing within the cathode particles, which results in performance fade. And then also the prolonged cycling can lead to particle cracking, as just shown down here, which results in increased surface area, along with more parasitic reactions to the electrolyte. It also can result in gas evolution and pressure increases, and this also can result in poor contact of the cathode particles with the overall laminate, which results in poor contact with the current collector, which can result in an increase in the impedance. So in general, if you start having the cracking, significant cracking of your particles and damage to the particles, as I said, this results in a damage to the overall laminate and usually results in an increase in the impedance or resistance of the cathode and also for the whole cell, because typically the cathode, after cycling and aging, is the primary source of impedance problems for lithium-ion batteries. So NMC cycling, when we investigate the NMC cycling with different nickel contents, what we can see is that by going from the 111 to the 523, which once again, these are ratios of nickel to cobalt to manganese, to the 523, to the 622, and up to the 811, we start to see a significant increase in the capacity as we increase the nickel content, which once again is why there's a significant interest in increasing the nickel content of these NMCs, outside of the fact that cobalt is very expensive and toxic. There's also an advantage in terms of the capacity of the materials. However, what you can also see is that while the capacity is increased, the rate of capacity fade is also increased. So as you go to higher nickel content, the rate at which you lose the original capacity you have increases as a function of the increase in nickel content. In addition, if you look at the electrochemical impedance spectroscopy, going from the NCM 111 to the 523 to the 622 and then to the 811, you see a steady increase in the overall electrochemical impedance of the cells, which is adversely affects the overall performance of the cells. So by going to higher nickel content, we both we increase the capacity fade, and we also increase the growth of the impedance of the cells. Now, what is the overall source of these problems? So with these cells, after cycling, we were able to take the cells apart and do ex situ analysis on the surface of the cells. And what you can see in these cases is that the surface of the cathode is very similar for all of the samples, regardless of the nickel content. And so therefore the capacity fade is not necessarily, directly related to the cathode surface film that is being generated from the decomposition of electrolyte. We also can tell if we look from XPS spectra that the anode surfaces for all of these different materials are also very, very similar. And the anodes contain low concentrations of both nickel, cobalt, and manganese. However, XPS is not really the best way to determine the transition metal content on the surface of the anodes. So we moved on from the investigation of just the direct investigation of the different nickel contents of NMCs to look at the effect of voltage or potential on the cycling performance of different NCMs or NMCs based cathode materials. And in this case, if we look at the NCM 111, so this is now 1/3 1/3, 1/3, nickel, cobalt, and manganese. And what we can see is that as we increase the potential from 4.2 to 4.5, we see a significant increase in the overall capacity of the cell. And we don't really see a very large difference in either the capacity retention upon cycling to 55 degrees centigrade or the efficiency. So we're getting the detrimental reactions of the electrolyte at high potential don't appear to be a significant problem for this NMC 111 material in terms of the capacity, as I said, the capacity retention or the efficiency. However, we see very large increases in the impedance at higher potential. So for the cells that are cycled to the 4.5 volts, what we can see is a full cell, we have a much larger impedance after formation or after cycling at 25 degrees centigrade, and even a larger one after cycling at 55 degrees centigrade. However, if we take these cells and take them apart and build cathode-cathode or anode-anode symmetrical cells, what we can do is isolate the electrochemical impedance to changes to just the cathode or just the anode. And what we can see here is that the changes on the anode side are relatively small for all of the cells cycled to the different voltages, while the changes on the cathode side are very, very large. So what this tells us is that most of the impedance growth of the full cells is due to increased impedance on the cathode. The cathode is the source of the impedance growth of these cells. So if we go back and investigate the surface of these NCM111 cells by XPS spectroscopy, once again, the surface metal oxide concentration decreases upon going to higher potential from the pristine to the 4.2 volts. And if we go to the 4.5 volts, we see even a greater decrease in the overall concentration of the metal oxide. So what this suggests is going to higher potential results in electrolyte decomposition, increased concentration of electrolyte decomposition products, which may correlate somewhat with the increased impedance, but yet we didn't observe a significant capacity loss or efficiency fade. The anode SEI is quite similar for cells cycled to either 4.2 or 4.5 volts, and there's low concentrations of transition metals for all cells. However, there's not really a clear trend in terms of transition metal deposition on the anode and the potential that the cathode is cycled to. If we look at IR spectra, once again, the IR spectra of the anode is quite similar for all of the cells, for the cells cycled to either voltage, while the IR spectra of the cathode shows significantly more electrolyte decomposition upon cycling to 4.5 volts compared to the one cycled to 4.2 volts, which is consistent with the data that we observed from XPS spectroscopy. What this suggests is there's a thicker surface film for the cell cycled to higher potential, but there's a small difference in capacity fade. However, once again, on the cathode side, there is still a large increase in impedance. And it's unclear if the increase in the impedance is due to the fact that we're generating a thicker surface film, or if it's due to other issues such as particle cracking or problems with the laminate on the cathode surface. So if we move up in nickel content to the NCM622, we can see that we also, by increasing the nickel, by increasing the voltage from 4.3 volts to 4.6 volts, we observe a significant increase in the capacity. However, we also see a very large increase in the capacity fade upon cycling to 4.6 volts compared to cycling to 4.3 volts. This can be observed both in the capacity versus cycle number, and we can also see this in the charge-discharge curves, that upon cycling to larger, higher potential, we get the more capacity. However, after 100 cycles, we see a significant amount of both voltage fade and also capacity fade in these materials. And there's not a large difference between the discharge capacity of the materials after 100 cycles for those cycled to high voltage versus those cycled to the lower voltage. If we go back and look at the electrochemical impedance spectroscopy for these cells, what we can see is that there's a higher initial impedance after one cycle. However, there's a very large increase in impedance after cycling. So basically, while there's a small increase in impedance after the first cycle, after 105 cycles, we see a much larger impedance growth for the cell cycle to higher potential, which is quite similar to what we observed for the NCM 111 cells. If we take these cells apart, and in addition to trying analyzing the surface of the cathode materials, we try and analyze the electrolyte itself. Because we were this time trying to understand better the role of electrolyte in these decomposition reactions. And we also were trying to determine a diagnostic where we could easily look at something and go, oh, this is going to be a problem for the cell if we see the observation of these kinds of decomposition products. And we thought that the change in the electrolyte, the decomposition of the electrolyte, or the trans-esterification reactions of the electrolyte, where we start off with all ethyl methyl carbonate, and over time the ethyl methyl carbonate undergoes disproportionation reactions to generate dimethyl carbonate and diethyl carbonate. So we thought that this disproportionation reaction would be a good tag to look at in terms of understanding and predicting capacity fade in these cells. However, when we cycle the cells to the high potential versus the low potential, we basically see very little difference in the concentration of these trans-esterification products, and also relatively small differences in the generation of oligocarbonates. So in addition to the trans-esterification reaction, you also can have trans-esterification reactions with ethylene carbonate, which results in a polymerization reaction or an oligomerization reaction. And once again, these are bulk decomposition reactions of the electrolyte. However, there's very poor correlation between these electrolyte decomposition reactions, both after the first cycle and after 50 cycles, with the performance fade of the materials. So we don't really see more electrolyte or carbonate solvent disproportionation reactions at higher potential. So if we move up from the NCM 622 material to the NCM 811 material, once again, we see even a larger increase in the capacity upon going from 4.2 volts to 4.6 volts, but nonetheless, we still see a very large capacity fade for the cathode materials that are charged to the higher potential. If we look at the QDV plots for these materials, what we can see is that there are significant changes for the materials that are cycled to 4.6 volts and only very small changes for the cells that are cycled to the 4.2 volts. Once again, what this is telling us is that there's changes and there's decomposition reactions within the cathode, the bulk cathode materials, upon these charging cycles. If we look at the electrochemical impedance spectroscopy of the 811 cells, we see trends that are very similar to what we observed for the 622 and the 111 cells. After the first cycle, there's a small difference in the electrochemical impedance for the cell cycle to 4.2 versus the cell cycle to 4.6. However, after cycling 100 cycles, we see much greater impedance on the cell cycle to 4.6 volts than we do for the cell cycle to 4.2 volts. When we go back and we build symmetrical cells after one cycle, what we see is, once again, there's greater impedance on the cathode side and smaller impedance on the anode side, suggesting that these impedance changes are predominantly, once again, due to changes on the cathode side and not due to changes on the anode side. So if we go and do online electrochemical mass spectroscopy in collaboration with Hubert Gasteiger at TU Munich, once again, as we observe the generation of trans-esterification products, so once again, we started off with EMC as the electrolyte, and we see trans-esterification of the EMC to generate both DEC and DMC. However, there's virtually no difference in the trans-esterification species, the concentration of the trans-esterification species for the cell charged to 4.2 volts versus the cell charged to 4.6 volts. The largest difference is we see much more CO2 evolution for the cell cycle to 4.6 volts, and we also start to see oxygen evolution at these higher voltages. So if we only cycle to 4.2 volts, we basically see no oxygen evolution. However, as we cycle to a higher potential, we start to see oxygen evolution and also more carbon dioxide evolution. But in terms of the bulk electrolyte, we don't really observe any significant changes to the bulk solvents under these conditions. We go back and do our same extractions and do GCMS of the extractions. Once again, we see large increases in the transesterification products on the first cycle, but there's not really a significant difference between the cells cycled to 4.2 volts and the cells cycled to 4.6 volts. And if we continue cycling the cells for the different voltages up to 100 cycles, what we see is basically no significant difference in the overall concentration of the oligocarbonates, transesterification products, or of the transesterification products of the dimethyl and diethyl carbonate. So basically the changes are small with additional cycling. We have a lot of it initially. As we continue cycling, the concentration of these species does not significantly go up. And once again, there's not really a large difference between the generation of the transesterification products at both 4.2 volts and 4.6 volts, which is consistent with what we observe for the graphite NCM622 cells. So if we look at the XPS spectra of the graphite anodes extracted from these NCM811 cells, or the XPS spectra of the cathodes extracted from the 811 cells. In the case of the cathodes, we see very, very similar XPS spectra, suggesting that there's no changes to the cathode surface film with increased potential, which is what we also observed with the 622 cells. However, what we also observe on the anode side is a significantly thicker anode SEI for the cells that are cycled to higher potential. And so you can see this, that basically there's more of the electrolyte decomposition products in the case for the cell cycle to 4.6 than in the cell cycle to the 4.2 volts, which is once again consistent with more transition metal dissolution from the cathode and being deposited on the anode, or also more electrolyte oxidation to generate acidic species on the cathode that then decompose the anode SEI. And so with that, there's been several proposed mechanisms for the overall performance fade of NCM cathode materials. And this is from a manuscript published in the Journal of the Electrochemical Society by Daniel Abraham and coworkers. And basically, this first stage of the decomposition results in the fact that we have transition metal content, which is dissolved from the cathode, which then goes over into the anode, and results in a net decomposition or degradation of the anode SEI. However, this also could be related to the generation of trace acidic species on the cathode surface. In addition to these reactions, the NMC particles are cracking. The NMC phase transition, not the cathode electrolyte interface, correlates with the cathode impedance rise and also a lot of the performance phase. And so most of the impedance growth we have observed is likely not due to the reactions of the electrolyte, but is due to the particle cracking, the NMC particles cracking and resulting in a damage to the cathode laminate and an increase in the impedance. It's also interesting to note that the surface impurities such as lithium carbonate or surface modifications such as alumina can significantly inhibit the transition metal dissolution on the cathode and also the damage to the anode, to the SEI on the anode, but the mechanism of this remains fairly elusive. And also a lot of electrolyte additives have been developed which offer a similar benefit to these alumina surface coatings on the cathode. So, as I've mentioned already, the electrolyte oxidation on the cathode can not only result in transition metal dissolution, but there's also been reports that the electrolyte oxidation on the cathode generates acidic species. So this was an investigation by Hubert Gasteiger and coworkers, where they investigated an EC-LiPF6 electrolyte with a carbon black electrode. And what they observed was at relatively moderate voltages, 4.5, 4.6 volts, they start to generate phosphorus oxyfluoride, which is a very strong Lewis acid, the same decomposition product that's observed from the thermal decomposition of LiPF6. This is generated at high potential from the oxidation of EC and then the subsequent decomposition of PF6. So the fact that we have both ethylene carbonate and PF6 together allows this oxidation reaction of ethylene carbonate to be coupled with the thermal decomposition of PF6 to generate the phosphorus oxyfluoride. And this initial generation of phosphorus oxyfluoride, or this initial electrocatalytic generation of phosphorus oxyfluoride, can initiate this autocatalytic decomposition of the electrolyte to generate more phosphorus oxyfluoride in the electrolyte formulation. And if we look at the electrochemical performance of the NMC811 graphite cells as a function of the electrolyte additive, what we can see is we look at the standard electrolyte formulation, LP57, compared to the electrolyte formulation with propane sultone or lithium difluorophosphate or succinonitrile, we see basically fairly similar capacity retention for all of these cells. However, in the case of the lithium difluorophosphate, we see a very low impedance. However, we see fairly similar impedances for both the propane sultone, the standard electrolyte formulation, and the succinonitrile. So while we have slightly higher initial specific capacity, there is really comparable capacity fading. The only real difference we see here from the electrochemical cycling is that the lithium difluorophosphate reduces the impedance on the cathode. With this in mind, if we look at the OEMS, online electrochemical mass spectroscopy data for all of these different electrolyte formulations, with the LP57, we see a large amount, as we said, of transesterification products and a fair amount of carbon dioxide evolution. Incorporation of propane sultone significantly decreases the evolution of ethylene and also significantly decreases the concentration of the transesterification reactions. Alternatively, the lithium difluorophosphate completely inhibits the transesterification reactions, completely shuts them all down. And also, CO2 loss, it inhibits CO2 somewhat. And then finally, succinonitrile doesn't really alter the gassing of them at all. And also, it's also interesting to note that none of these electrolyte additives really affect the oxygen evolution. If we go back and we look once again at the GCMS analysis of the transesterification, much like what we saw with the OEMS analysis, the addition of propane sultone and lithium difluorophosphate basically completely shut down the transesterification reactions. However, the other species, we see relatively high concentrations of transesterification. So it's really very, very confusing with these different electrolyte additives, which have been most all of them have been reported as good high voltage electrolyte additives for cathodes. We see, very different features in terms of how they alter the chemistry of the cell, in terms of both the transesterification reactions and the gassing reactions. But there's really very poor correlation between how these electrolyte additives change the cell chemistry or the electrolyte chemistry and the overall performance changes of the materials or of the cells. If we go back and we look at the ICP-MS analysis of the graphite electrodes for the standard electrolyte formulation, basically all of our different additives result in significant decreases in the transition metal dissolution, both after 1 cycle and after 100 cycles. So all of the additives are inhibiting transition metal dissolution, but there's really no correlation between transesterification reaction, where lithium difluorophosphate completely shut down the transesterification reaction, but it doesn't really shut down transition metal dissolution, and none of these things really correlate with performance fade. And also, unfortunately, with our XPS analysis, was quite similar for all of these different electrolytes. And so I would say, while there certainly have been a lot of reports of different electrolyte formulations that improve the performance of NMC cathodes that are cycled to high potential, it's very elusive understanding what the mechanism of these electrolyte additives are at inhibiting these reactions and in stabilizing the cells. Once again, these difficulties in correlating things has also been previously reported by Jeff Don and coworkers. And in this case, these electrolytes, which contain both FeC and DTD, which is a sulfur-based additive, what they observed was that there was a very poor correlation between the dV/dV, which is the change in voltage with voltage, and also the capacity fade here. with either the trans-esterification reactions or also the transition metal dissolution. So once again, what they observed is as they went to higher and higher voltages from 4.0 volts to 4.1 to 4 up to 4.4, what they see is basically an increase in the overall resistance, which is this dV plot. They see a decrease in capacity, or we see worse capacity fade at higher voltage, consistent with our results, but yet these trans-esterification reactions do not really correlate with potential increases, and nor does the transition metal dissolution. So once again, trying to understand what the sources of these capacity fades are in these NMC materials as a function of electrolyte reactions is quite complex, we'll say. So as a summary for the NMC materials, the cathode electrolyte interface has a poor correlation with impedance growth or capacity loss. The trans-esterification of carbonates also has a poor correlation with impedance growth or capacity loss. The transition metal dissolution, manganese and nickel, might correlate with the anode SEI thickening and capacity loss, but it's not necessarily clear. It's also important to recognize that in NCA there is no manganese, and so we're not going to see there's not going to be manganese dissolution here. Oxygen evolution does not appear to be inhibited with any of these electrolyte additives. And also it's important to know that the NMC washing procedure and or surface modification will clearly modify reactions with the electrolyte. So, however, it's also important to recognize that electrolyte oxidation to generate acidic species such as phosphorus oxyfluoride and PF5 and HF may lead to SEI degradation and capacity loss. And both electrolyte additives and cathode surface films can inhibit the generation of these acidic species in the electrolyte, and they also can inhibit transition metal dissolution. With this brings us to the final section of cathode materials, which is the lithium-rich layered metal oxides, or high-energy NCM materials, which is depicted by this molecular structure. These are very promising candidates for the next generation of lithium-ion batteries, primarily due to the extremely high capacity, 240 milliamp hours per gram. This is, most of your NMC materials, even with high nickel content, are more so around 200 milliamp hours per gram. And so this is a significant improvement in the overall capacity of the material. However, these materials have both significant problems with voltage fade and also capacity fade. The voltage fade is typically attributed to the bulk structural changes of the layered metal oxide, and the capacity fade is typically attributed to surface reactivity. And we will focus my presentation on the latter part here, which is the capacity fade, because most of these surface reactivities are typically related to the reactions with the electrolyte. So if we look at the overall capacity retention for these high energy NCM graphite cells, what we can see is that if we now compare the uncoated high energy NCM compared to alumina coated, as I mentioned previously, outside of the development of electrolyte additives, one of the other ways that people are improving high voltage or high energy cathode materials is by coating the surface of the cathode material, which can inhibit reactions with electrolyte. And what we see here is either the cycling at 25 degrees centigrade or the cycling at 40 degrees centigrade, the alumina coating provides a significant improvement in the overall capacity retention. And what we were interested in doing was developing a better understanding of how these alumina coatings impart improved stability and improved capacity retention of these cells. So if we look at the electrochemical impedance spectroscopy, for the graphite symmetrical cells, which are extracted from the high energy NCM materials, what we can see is after the first cycle, there's relatively low impedance growth, while after the 20th cycle, we see more impedance growth, and then after the 50th cycle, the uncoated cell has much, much larger impedance than we observe with the aluminum coated, the alumina coated cathode. So once again, we see a significant impedance and impedance growth for the cells that with the coated cathode materials. If we go back and do XPS analysis of the high energy NCM materials, and in particular, if we look at the surface of the cathode, what we can see is the surface films are similar for both the high energy NCM coated alumina However, the NCM-coated alumina has more of the metal oxide present. So if we look at the uncoated species and we start off with the first cycle, we have a fair amount of metal oxide. As we continue cycling, we see a lot of electrolyte decomposition, and the relative concentration of the metal oxide is decreased. However, in the case of the alumina-coated material, we see much less generation of electrolyte decomposition products on the surface, and we see significantly more relative metal oxide being retained. So what this is consistent with is basically less electrolyte deposition on the alumina-coated surface, which suggests that the alumina coating may inhibit the detrimental reactions with the electrolyte. If we also look at the graphite surface, what we see is smaller changes to the SEI on the aluminum-coated material. And so with the uncoated material, we see very large changes. After the first, 20th, and 50th cycle, we see large growths of electrolyte decomposition by both oxygen and carbon spectra. While in the case of the alumina-coated, we see only small changes to the surface of the graphite, which once again suggests that in the presence of the alumina, we're inhibiting the decomposition reactions of the electrolyte with the surface of the graphite. So the alumina is inhibiting either the generation of the acidic species, the phosphorus oxyfluoride on the cathode, or the alumina is inhibiting transition metal dissolution from the surface of the cathode. And either of those species can potentially damage the surface of the anode or the anode SEI. If we look at the elemental concentrations, once again, they're similar for the high energy NCM surface, but we see more fluorine on the anode surface for the uncoated cells. So once again, if we look here at the cathode surface, basically after the first, the 20th, and 50th cycle, we're not seeing really large changes with either the uncoated or the alumina coated. We see not a lot of changes to the surface of the cathode. However, on the anode side, for the alumina coated material, once again, we do not see very large changes going from the first to the 20th to the 50th cycle. However, in the case of the uncoated surface, we see very, very large increases of, in particular, fluorine, which the presence of fluorine is consistent with additional electrolyte decomposition products, which could result from either the transition metals damaging the anode SEI or from the generation of phosphorus oxyfluoride at the cathode surface, which then transports across from the cathode to the anode and subsequently damages the anode surface, the anode SEI. If we look at the FTIR spectra, once again, the high energy NCM surfaces are pretty similar, the IR spectra of the cathode. However, the graphite from the uncoated cell has much more polycarbonate right here, which is consistent with a thicker surface film and more electrolyte decomposition on the surface. If we look at the transition metal content on the anode, which once again is a characteristic frequently of the decomposition reactions on the anode, for the uncoated sample, we see relatively high concentrations of manganese, cobalt, and nickel after the first, 20th, and 50th cycle. However, we see significant reduction in these transition metal contents for the alumina coated, which once again suggests that the aluminum coating is inhibiting transition metal dissolution. Although it's also interesting to note that a large quantity of the transition metal is being generated on the first cycle of these materials, which is somewhat different than with the traditional NMC materials. And this may be related to structural changes that occur during formation cycling of these high energy NCM materials, which this formation cycling of the high energy NCM materials is really a very critical and important aspect of these interesting cathodes. And so the conclusions for the high energy NCM is that the alumina coating on the high energy NCM improves the cycling performance of high energy NCM graphite full cells. Ex situ analysis of the high energy NCM and the graphite electrodes reveals that the surface chemistry of the high energy NCM is not significantly altered with the alumina coating. However, the surface chemistry of the graphite is significantly affected. The alumina coating on the cathode improves the anode SEI stability. And once again, this could be either due to the alumina coating inhibiting the generation of acidic species on the cathode, or the alumina coating inhibiting transition metal dissolution from the cathode, or both. The transition metal dissolution or anode generation of the cathode surface catalyzes additional electrolyte decomposition on the graphite surface by decomposing the anode SEI. And the improved cycling performance can be attributed to the prevention of this transition metal dissolution and the acid generation from the high energy NCM. And so overall, for all of these cathode materials, we believe there's kind of a similar trend in terms of how these cathodes that are cycled to high voltage or NMC cathodes with high potential or high nickel content are degrading. And a lot of it relates to damage to the surface of the anode and to the SEI on the anode. And there's basically two different mechanisms that have been proposed for this. One is really focused on transition metal damage to the anode SEI, and the other is focused on the damage to the anode SEI by the presence of acidic species, such as phosphorus oxyfluoride. And so in the case of the transition metal damage, the transition metals can catalyze the decomposition of the SEI and also catalyze more electrolyte reduction on the surface of the anode. And in the case of the acidic species, basically the acidic species can come in, react with the SEI components, such as lithium ethylene dicarbonate. These acidic species can decompose these Lewis basic SEI components, such as lithium ethylene dicarbonate and lithium carbonate, which results in the damage to the SEI, the dissolution of the SEI components, and the evolution of CO2 gas. And so basically, the overall combination of the transition metal catalyzed decomposition of the SEI and the acid-induced decomposition of the SEI in the anode are two of the likely sources of increased capacity fade for cathodes cycled to higher potentials, or also cathodes with NMC cathodes with higher nickel content. And so with that, I'd like to thank all of my students who conducted the research. And in terms of the presentation here, a lot of the earlier work on the high voltage spinel materials was conducted by Moon Ching and by Julian. And a lot of the later work on the NMC and the high energy NMC materials was done by Nina and by Sun Young. And once again, I'd like to thank all of you for listening to my presentation. And with that, let me stop sharing the screen. And once again, so this is the end of the series of 4 lectures on lithium-ion batteries. And once again, the first lecture was kind of an overview of lithium-ion batteries, just how lithium-ion batteries perform, some aspects of the manufacturing, and a general coverage of both the cathode materials and the anode materials that are utilized in lithium-ion batteries. The second presentation was a general overview on electrolytes. And then the third presentation was on the reactions of the electrolyte with the surface of anode materials. And then this final presentation has been on the electrolyte reactions with the surface of cathode materials. And once again, I would like to thank you all for listening to my presentations, and I hope you enjoy your day.